Hello, in this video we're looking at a bacteria in a certain culture. So that's like a petri dish with some sort of food in it for the bacteria, and it will double, that's a key word, underlining that, every 1/2 hour. We're going to assume that the culture has 100 bacteria at the start. So step one in this process is to write an equation for this scenario, and we're using the formulas that are on our pre-lecture. So based on that keyword double, I'm focusing in on the doubling time model, which says P of t, population at some point in time, is P0 starting amount times 2 to the t over d exponent. That times 2 is because of doubling is multiplying by 2. So for this scenario, we will keep P of t as a variable. P0 we will replace with 100 bacteria. That will be multiplied times 2. In the exponent, we will keep t. Time is a variable, and we can check on the population at any point in time. But the doubling time does need to be filled in, so the d needs to be replaced, and I'm going to use decimal here, 0.5 hours to represent the half hour. So that is my equation for this scenario. Question number 2. How many bacteria will there be in 4 hours? So 4 hours is a time, and I'm going to plug that into my formula where the t is. And so for this one, I'm calculating the population, which is something that can be done on a handheld calculator. So writing this over, time is 4 divided by 0.5. Now, we could do the math in the exponent, and that would come out to be a whole number, but our calculator can handle this, so I'm going to just type it as it is. So I will type 100 times 2, caret key, parenthesis, 4 divided by 0.5. And so I'm going to type that in, and I encourage you to do the same. Go ahead and type and make sure that you are able to execute that exactly as you want to. Sometimes it's like, it looks like it makes sense, but then when I go to do it, I get a different answer. So make sure you're getting the right answer. We do get a fairly large answer here for P of t, the population, because the bacteria is indeed growing and rather rapidly, doubling every half hour. So my calculator gave me P of t equals 25600. I'll come back and put a comma in, so 25,600 bacteria. And so then we can move on to our third question. And it says, how long will it take until the culture has 500,000 bacteria? So this question of how long is asking me to find time, and that means that I need to use decimals. Or I can do a logarithm by hand. Either method is fine by me, even though I'm demonstrating decimals in this video. So going back to my formula, this 500,000 is a value of the population at some point in time. So 500,000 equals 100 times 2 to the t over 0.5. Decimals is going to require we have two formulas. So this side of the equation, the left-hand side, can be rewritten as y equals 500,000. And my right-hand side, this side, can be written as the formula y equals 100 times 2 to the t over 0.5. So I go and get decimals. And I'll change my first equation here to 500,000, 500,000. And I'll change my second equation here to be y equals 100 times 2 to the, and I like to use the parentheses here, even though I don't think it's required. And so we have here x, because decimals prefers x, divided by 0.5. I'm arrowing over and ending my parenthesis. So I have a graph here, and I'm not seeing a good window on it. Like I can see a curve going almost straight up, and I don't see my 500,000 line. So this one, it can be a bit of a challenge to find exactly the right graph. But I'm going to start by zooming out. So I'm still seeing that black line that looks like a right angle now going up. I'm going up. Finally, I get to where I can see my 500,000. And so there does appear to be a dot here. And as I point at that dot, so this black line, which is like literally right on top of my axis, and that dot is the number that I want. So 6.144 hours. So let me move Desmos out of the way. And so this is telling us ordered pair 6.144 hours, comma, 500,000. And so in that, the X is the one that we wanted. The Y value is what we had typed in. And so the time in this problem is 6.144, or you could say about 6 hours. Now I want to bring back our graph for a moment, and I want to show you something that might help you with this a little bit when you have a problem like this. We did find our answer because we were able to find that point where they intersected, but we really can barely see our exponential curve anymore because our x's are zoomed out so far. So if we click on this little wrench here, which says graph settings, you can see that it allows the settings to show for the X and Y axis. And so we had to zoom out so that we could see 500,000 on the Y axis, but we don't need to be nearly so zoomed out on the X axis. So my answer is positive 6. So I'm going to change this. So delete that, to go from negative 10 up to, delete this whole side, positive 10. And so that's just a whole lot more zoomed in, and then I'm going to close the wrench. And now I see a very nice exponential curve coming up, going up to this 500,000. And if I click on one of my curves, it again shows me the exact same point we had before. So it's not essential that I do this, but it just looks so much better to me because I can see the exponential curve. I see the line coming across, and I know that I have the actual graph, and I'm not just looking at where does the line cross the axis, which would not be the ordered pair that I want. And so it gives me confirmation that I do have the right pair. And so if you want to zoom specifically to see more detail, this wrench, so it's called graph settings when I go to it, allows me, and I could have changed both X and Y. I was okay with the Y axis because that's why I had zoomed out so far. It was really the X axis that was way too big. And we could have set this knowing that we had a positive number for our answer to have started at 0 and go 0 to 10. And if we look at that graph, it's even a nicer picture of this curve here, this beautiful exponential curve of bacteria growth. And then we can find this answer, and I can even see that it's just a tick beyond 6 hours, and I'm able to see that detail that I wanted. So in summary, another problem where we did all 3 steps, all 3 outcomes for this lesson. We wrote the formula, we did the formula on our calculator, and that's any time that we want to know the population. And then we used the Desmos calculator to solve for time using the graph there. You could have also done that last part with a logarithm.